Hi everyone and welcome. Thank you for joining me. So tonight I want to build the Jupiter simulation, or more generally the gravity simulation that we discussed on a pseudocode level. And so I would like to start by pointing out the three folders that we're going to need that I provided as starter code. So I provided a Jupiter folder that has 3 Go files within it. I provided also a folder called Canvas and a folder called Gif Helper. Now inside each of those folders you will notice a file that we actually have already worked with previously. So when we built Cellular Automata, we had a Canvas file that was provided that allowed us to kind of draw objects onto a canvas, and we had a Gif Helper file that communicated with some code that had been written to help us produce from a collection of images an animated GIF. And so I want to show how we can use these as separate pieces of code, because we may have use for both of these functions or these kind of pieces of code in more broad contexts than just doing cellular automata. So we're going to use them when we want to visualize the moons of Jupiter as well. And so what we're going to do then is, rather than having to move canvas.go and gifhelper.go around, we're going to have them as separate files within separate folders. And I want to just call them whenever they're needed. And this is much like, say, if we want to print information to the console, we use an FMT package in Go, and we don't want to have to write all the code ourselves in order to just print something to the console. So in this case, it's generic code that we would like to reuse. And so anytime we have functions that we would like to reuse, we want to be able to build our own packages. And so this is the idea of me providing gifhelper.go and canvas.go within each of their own files or own folders. So if you take a look at this canvas.go file, you'll see that I've added an acknowledgement, but I've also added the statement package canvas to the top of this file, and it has the import statements, and I haven't altered this file otherwise, but we have a package canvas statement. So what that says is, if I want to call any of these functions that I find here, so if I want to create a new canvas, or if I have a canvas, I want to set the fill color, or create a rectangle, or draw a circle on the canvas at a given point, I'm going to be able to do so. I'm not going to need to drag canvas.go around. I can just have it in one place, which is in the canvas folder, and I'm going to be able to install it as its own package if I have the statement package canvas. Okay, so the way that we are going to install a package in Go is to navigate to the folder that contains the code that we want to reuse. And so in this case, it's in the Go src canvas directory. And once I get there, I need code that will compile. But if I call go install, that will take the code that I've written and compile the code, and so that all the functions within this file have already been compiled for us and are ready to be reused whenever we like. And so you'll notice that we have a PKG folder, and if we look within it, we'll see that we have canvas.a, where we have pre-compiled canvas functions where everything's good to go. We know there are no syntax errors, and we can use these canvas functions whenever we like. I would like to also go up a directory in our navigation and navigate downward into the GIF helper. So the gifhelper.go file is here. And so that contains a couple of functions that I'm providing. One is an images to GIF, which takes a slice of image objects from the image package. So that's why we have the image dot they come from the image package, and they're called images, image objects. And it will produce an animated GIF with the given file name. And so it doesn't return that, it simply produces it, writes it to the file, and it uses this image to paletted subroutine that I have that's going to do kind of this image processing behind the scenes for us. So I don't want to focus too much on the image processing here, but I do want to point out that in practice, if I have a slice of image objects and the file name that I would like to write them to as an animated GIF, then I can call this function images to GIF, and it will write them with the file name.out.gif. So I want to install this code as well so that I can use this images to GIF function whenever I like. And so I'm going to cd into Gif Helper from src, and I'm going to install that package also, and that produces within the pkg directory, you'll be able to see that this package, which, note I've got package Gif Helper. This has been produced as our own package. So now, just as if we import math/rand, I can call rand.int. If I import fmt, I can call fmt.println. Now I'm going to be able to import Gif Helper and import canvas. And if I call canvas dot whatever function, or canvas or Gif Helper dot whatever function we like, here images to GIF is what we're going to use, we're going to be able to use them from whatever other directory that we're in, so we don't have to constantly move these around. Okay, so that's all I would say about those two files. Next, I would point out, let's look at Jupyter. And I have produced 3 files within the Jupyter directory. In the meantime, I'm going to navigate into it. So I'll go up a level with cd ... and then I'll navigate into my Jupyter directory. And so I'm ready to run the terminal here. In the meantime, I'm going to open all of my .go files here and take a look at them. So I have a main.go file, I have a gravity.go file. I'm just going to have my gravity simulation functions in this file. I'm declaring package main here since this is going to be a runnable program. And if I wanted to have a gravity package where all these functions went into the gravity package and they could be called from different folders within our Go SRC directory, that would be fine. But I think for now I'll just have everything, everything will be package main. And so this will be a runnable program that's divided over 3 .go files. Drawing.go is going to be where our drawing functions go. And so I'll describe those when it comes time to animate our system. And main.go is going to have the overall data setup for what we want to do now that we're moving towards object-oriented programming. And that will be where we actually run our program. So I'll walk through main.go for now, since it's the only place that we have code currently. And so I've got an import math and an import FMT declarations. We're going to need some math if we're going to build a physics engine. I probably should actually move those over to the gravity.go file when we need them. I'm going to declare the gravitational constant in the gravitational force equation. So this is 6.67408 times 10 to the negative 11 approximately, and we'll see that that's a good enough approximation. Now I'll make a brief few remarks about how we declare our own object type in Go. So I discussed this on a very high level with pseudocode, where we think of an object as containing each of a collection of fields. And so each field may have its own type. For something like a body, we said, well, it needs to have a name, that's a string. It needs to have a mass and a radius. That's a float 64 if we're assuming circular bodies. We may have a position, a velocity, and acceleration. And last time we saw that we represent each of those in terms of its components. So position will be represented as its x and y coordinates. But velocity and acceleration will be represented as its x and y components as well. Then I'm going to have a red, green, and blue field as well. In this case, so for a given body, I'm going to let it have a color, and that color will be formed of certain amounts of red, green, and blue that are mixed together, these being the primary colors of light. And so if we have, only red, then we would have a maximum amount of red, or a maximum amount of green for green. But if you start mixing these colors, you mix, say, all of them together, then you get white, which is the kind of what happens when you mix the three primary colors of white, since this is primary colors on the level of light as opposed to paints. So we have addition as opposed to subtraction. I don't want to get into the details too much of how colors are represented, at least at the current time, but I'll point out that the declaration for a body object is similar to how it was covered on a pseudocode level. So we have a type, we declare the name of the type, which is a body, and we use struct to indicate that what is being declared is an object. And then the struct, just like many other things, is enclosed in brackets. And I could represent each field on its own line, but I've joined together with commas fields that have the same type. So we have this shortcut way of declaring a body. So where there's one field of a body that's a name, that's a string. Okay, mass and radius are both float 64s, and so on. So this is very similar to what I saw presented already on a pseudocode level. We also see kind of the top-down organization of the object types too. So a body has position, velocity, and acceleration as ordered pairs, and that's an object itself. So we have a type ordered pair struct, where that object consists of an x and a y. So we have an x component or an x coordinate and a y component or a y coordinate, as the case may be. In each case, we want to allow a decimal, so we have float 64. The only other thing to say here is that a uint 8 will be when we need to communicate with color. This will allow values between 0 and 255, which is how color is standardly, I don't think is a word, but represented typically. So the red value, so if you think of a given pixel on your computer screen, you will have a certain amount of red that ranges from 0 to 255, a certain amount of green that ranges from 0 to 255, and the same for the level of blue at that current pixel. So that's how that will help us communicate with kind of how Go is representing color, so it can display or color objects on our screen. And then we have a universe type. And so we said before, the universe has a certain width, okay? And that width will be in terms of kilometers. And so everything here will be in kind of standard SI notation or units. And then we have a body's slice of body objects. So we have kind of three layers of this. We have a universe that has a width and has a collection of bodies associated with it. Then we have a body object that has a collection of its own fields, and then we have an ordered pair object that just consists of an x and a y, float 64. And I've produced main already, so kind of setting all the fields of our objects, I'm going to provide to you, but I'll walk through quickly. So I've declared, this is a shortcut so that I don't have to have 5 lines. I'm going to declare Jupiter, Io, Europa, Ganymede, and Callisto as our 5 bodies. I'm going to set each of their names. So remember, kind of the generic way that I've presented as setting a field is to say whatever the name of your object is, dot whatever the field is, and setting it equal to whatever you would like it to be. So I'm setting the names of each of these. So Europa.name, for example, is the string Europa, since we know that the name field is a string, has string type. Then I'm going to set the colors of these. So we can, and this is just me looking at kind of pictures of each of the 5 objects and taking an approximation of what color they are. So here we have Jupiter is 223 red, 227 green, and 202 blue. So that means we're mixing a lot of colors together, but we're also mixing them equally. And if you look at Jupiter, you see something that's very light in color. So it's closer to white, although not completely there. We have less of the blue channel when we look at Io, and we'll be able to see these soon when we visualize it. But these are just, you know, kind of tentative values for each of these 5 bodies. We're setting the mass of Jupiter, and these are, at this point, I've just pulled these from tables that are available. So I'm using the math package here to represent kind of a power of 10. So Jupiter has a lot more mass than each of the moons, although they each have their own, you know, significant mass. Ganymede being the most massive at 1.4819 times 10 to the 23rd kilograms. So we have a radius of Jupiter. And excuse me, I should have said that the SI unit is not a kilometer but a meter. And so this is the radius of Jupiter in meters. So we have 71,000 kilometers, which sounds right, very large. And then we have the radii of the corresponding moons as well, which are much smaller. I'm then going to have the positions of each of these. So I'm going to have a width of my universe. I should scroll down. So I have my width of my universe is, well, that's thousands and millions, and so it's 4 billion meters, all right, or 4 million kilometers across. I'm going to put Jupiter in the dead center of it. Okay, so rather than a 4 here, I've just set the position of Jupiter to be 2 billion meters in the x direction and the y direction. So that's going to put it at the center of our universe. And then for the moons, I've put them kind of around the 4 corners. We could access current data and figure out exactly where they are, but for the purposes of this simple simulation, I'm simply going to put them at northeast, south, and west. So Io's position is going to have a negative value based off of its mean orbital distance. Okay, so in this case, it's thousands, millions, so 421 million meters away from Jupiter. And so how I've done that is to take the position of the x position of Jupiter, which and then subtract 421,600,000 from that. So we're kind of going in the westerly direction, and the y value is going to be the same. All right. For Europa, I've kept its x value the same as Jupiter, and then I've moved it north. So I've moved it north by 670 million approximately meters. Ganymede is going to be in the positive x direction with y the same as Jupiter's position, so it'll be east, and then Callisto will be to the south by, you know, about 1.9 billion meters. All right, so this will be enough. Callisto is the farthest of these moons out of the 4, and that should be enough to capture all 4 of the moons and Jupiter. If we have a essentially circular orbit, we won't be flying off of the grid that we're allotting. So I've set the color fields, I've set the name, I've set the masses, I've set the radii. And I thought this might be pretty tedious to type out and have you follow along, so I've just provided it to you. And then I've set the initial velocities. So there's actually a formula. If you know the gravitational constant, and you know the masses of the objects, and you know the radius, so how far out the object is, you can quickly find out at a given point what its speed is, kind of perpendicular to where it would fall. So if it's in orbit, perpendicular to, you know, the vector between the moon and Jupiter, it might be maybe traveling in that direction if it has a circular orbit. And that's how we're going to start this off. And so the velocity here is just going to be the speed. So for example, Jupiter's not going to be moving. It may move over time based off of the pull of the moons. We'll see. Hopefully not. Io, so remember Io I said was kind of in the negative x direction, so it was almost like to the west of Jupiter, since the x value was, you know, 2 billion minus 421 million. And Io is going to be traveling 0 in the x direction. So if Io is over here on the west, it's going to be traveling in this direction, kind of in a negative y direction. It won't have any x component at the start, but it will be traveling in this direction. And our hope is that our simulation will automatically pull it back towards the center. For something like Europa, it was at the north point, so we're going to have it go in a negative x direction at the start and hope that gravity will pull it back to the center. And so we started off at its orbital speed of negative 13,740 in the x direction and 0 in the y direction. All right, and so Ganymede will be traveling upward. So if Ganymede's over here, we'll assume it's going upward. And then Callisto, which is at the bottom, we'll assume is going in a positive x direction. All right, but has no y component. I've not set the accelerations, since that's what we're going to compute as we go. So I'm assuming that the accelerations are both the default 0 values, which are what they will inherit. And so now everything here has kind of had its field set. So all the fields of each of the 5 bodies that we're looking at has been set. We haven't set acceleration, but acceleration, as I said, will get 0 for x and 0 for y. We now declare our universe, so I'm going to call the universe Jupiter System. So how do we declare an object in Go? The same way that we would declare an integer or a string or a float 64. In the first sense, we would say var, var, so I'm declaring a variable. What's the name of my variable? Well, in this case, I could call it Jupiter System. And what is its type? It has type universe. And remember, the universe has 2 fields. It has the width, which I've set to be 4 billion, and it has the bodies. And so this is the one-line slice declaration. So I'm going to say I'm declaring a slice. I could have said Jupiter-system.bodies equals make a slice of bodies of length 5. So I could have had something like make a slice of bodies of length 5, and then I could have said Jupiter system dot bodies of 0 is equal to Jupiter, and Jupiter system dot bodies of 1 is equal to Io, and so on. All right, so note that all this notation is consistent with everything that we've done before. All I've added here is if I want to access the bodies slice field of Jupiter system, I could say Jupiter system.bodies, but I'm still going to make it be a slice of bodies, and then I'm going to update each of the appropriate values. However, there's a much quicker way of doing this, which is a one-line slice declaration, where I say, I want a slice of bodies, and what are the 5 elements of this slice? And so those are the 5 variables that I've declared corresponding to each of the bodies in our system. And so now we have this statement ready to implement Gravity Simulator. So I hope if we compile within Jupiter, everything should compile. And then I haven't used any of these objects really. I've just set the width and the bodies of Jupiter system, but it's ready to implement the Gravity Simulator, and it runs, and it's set all the fields and so on. And we haven't done anything, but we're ready to go. All right, so that's the high-level overview. I will say much more about object-oriented programming and all the cool things that we can do with it in a future lecture when we kind of take the next steps. But I wanted to get into the Gravity Simulator reasonably quickly, and to point out that we can go ahead and work with object-oriented programming without needing to know a lot of the syntax of how it's implemented in Go, since we know on a pseudocode level, here's how an object works. An object can be thought of as having these attributes called fields, and if we create an object of a certain type, then we can access its fields with this dot, so whatever the object name is, dot whatever the field type or the field name is. All right, so we should be ready to go. Now it's just a matter of doing 2 things. So first, we're going to write the functions that we need for the Gravity Simulator, and secondly, we're going to write the functions that we need for drawing, and pull in from Canvas and pull in from the GIF Helper packages that we've already installed, the functions that we need. Okay, so I will start writing our gravity functions in gravity.go. And I will start with a function called simulate gravity. So we have initial universe, and that's a universe object. And we're going to take a number of generations as an integer. And we have a time interval as a float 64. All right. And so I could say, if I'm being precise, simulate gravity, what does it do? This takes an initial universe as well as a number of generations and a time interval parameter. What does it produce as output? Well, it needs to return a slice of universe objects that correspond to actually running the simulation. And this gravity simulation is going to be run numgens over the appropriate number of generations. Estimated for the given time interval. Okay, so we're going to update the simulation for a given number of seconds. All right, so time is going to be measured in seconds here. And so my return type then is going to be a slice of universe objects. So we're going to declare our universes. And so just as we've seen before with the previous, say, cellular automaton simulation, we know how many universes we're going to need. So our time points, I could call them, is going to be a collection of universes. So I'm going to make a slice of universe objects, and this should have number of generations plus 1 universes in it. Down here, that's what I'm going to return. And first, I'll set the initial universe. So I'm given the initial configuration, which is in main what I've already set for the Jupiter moons, but could be for whatever system that you like. You could read data from a file, for example, with millions of asteroids or whatever you like. So time points 0 then is going to get the initial universe. And now I'm going to have my for loop. So I'm going to range an I, or whatever my favorite parameter or variable name is here, starting at 1, going up to numgens, increasing by 1 each time. And I'm going to set time points of I each time equal to what happens when I update the universe for a single generation. So I don't need the numgens parameter, but I need to pass in whatever my current universe is, as well as that time interval parameter. And so at this point, after I've set this, call update universe numgens times. Okay, so I have a for loop that will do that, and that will kind of give us this snapshot at each point of updating the universe as we go. And then we had an update universe function. So this is just recalling that we've done this on the level of pseudocode, but converting over to Go. And so we say update universe. What does it need to do? It needs to take a universe object and a time interval. So that's presumably in seconds, and returns our the updated universe simulated after the given interval. Okay. So I'd pointed this out on the pseudocode level, but it's worth saying again. The larger the value of the time interval that we do, the bigger the time step. And so because this is an approximation, the worse our approximation will be, but it will also be faster. So there's a trade-off here between the accuracy of what we do and how fast it will be. In the meantime, I'll start converting this over from the pseudocode that we saw to Go. So I'm going to take a current universe that is a universe object, and I'm going to take my time interval parameter as a float. And then I'm going to produce a new universe object as output. because I'm going to update the universe and put it into a new universe, I want to keep all the fields of the current universe, and I'm going to use those fields to update my new universe. So I want to copy over all the fields from the previous universe to the current one, and then edit these as necessary. Now there are going to be other ways of doing that, but I like kind of setting it in that way and then adjusting whatever parameters as needed. So to do that, I'm going to have a function called new universe is copy over all the parameters of the current universe. Right. And then, well, we need to say for every body in the current universe or the new universe, either way, update its fields. Okay, so for example, the names aren't going to change. The colors of the bodies aren't going to change. So that's useful information to just copy over. What is going to change is the position of the body, the velocity of the body, and the acceleration of the body. So I should say it's fields that will change. Okay, and that's position, velocity, and acceleration. Mass won't change, radius won't change, but position, velocity, and acceleration, of course, will. So I need to range over the bodies in the new universe. So I remember that the bodies in new universe will be contained in new universe dot bodies. Okay. So new universe dot bodies is a slice of bodies. Okay. I should say has type slice body and contains the bodies we want to access. So if I want to range over all the bodies, I should simply range over new universe dot bodies. If I know that that's simply a slice, I can do something like for I : range over new universe dot bodies. And that will range over every body in my universe. Okay, and so as I range over this, I'm going to say, let's update. So B is my current body. And so B is new universe dot bodies of I. So we're going to take the ith element in the new universe dot bodies slice, and that's what I'm going to access. So I'll say new universe dot bodies of I dot acceleration equals update acceleration of based off of new universe dot bodies of I, and I'm going to need to know the new universe as well. Okay, so in order to update the acceleration, this is kind of a long line, but in order to update the acceleration of a body, I'm going to need to compute the force of gravity that's acted on it. And so that updated acceleration will need to know all the bodies in the new universe since they're all acting on the body. And I need to know which one I'm actually accessing, which is the current body, new universe dot bodies of I. And I'm going to do the same thing for the velocity, except that to update the velocity, I don't actually need to know everything in the new universe. That's just to do the force computation. And so in this case, what I will need to know is the current body, and I need to know the time. So this is where I'm going to apply kind of the Newtonian equations that will update the velocity of an object and its position based off of its current velocity, position, and acceleration. And I should need to write an update position function. That will also need to know which body do you want to update and how much time should pass based off of the current position, velocity, and acceleration. Okay, so this is kind of the high level of the update universe function. And we've seen all this on the pseudocode level, but we'll need to write first a copy universe function. And then I'll separate these out so they're easier to see. We need to write our update acceleration function, update velocity function, and update position function. I will note that it's tempting to have an underscore b here where I'm not interested in ranging over the indices of the new universe.bodies slice. I'm interested in ranging over the bodies. The problem is that this will create a copy of the body that we're interested in, and so we might be updating the attributes of that body, and then that object winds up kind of getting tossed aside. And so for now, I want to just use for I : equal range over the new universe.bodies, and every time I want to access that body, I'm going to set new universe.bodies of I. That's the ith body. I'm going to set its fields. There will be a much easier way of handling this later that I don't want to focus on for now, because I think everything else with the code is going to be pretty straightforward and not going to be as bulky as lines like this. Okay, so anytime you see new universe.bodies of I, just think that's my current body B. In the meantime, I said let's write a function called copy universe, and that function needs to take the current universe that we want to copy. So it takes a universe object and it produces a universe object. All right, so we should say what it does. This function copy universe takes a universe object and produces a new universe object with all fields copied over. Okay, so I'm taking all the fields of every body in the current universe and I'm copying them over. I'm also going to copy over the width. So I need to declare a universe object called new universe. So again, you see Adam is providing this nice code for us where we say I'm declaring a variable, it's called new universe, it should have the universe object type, and then at the end I'm going to return this new universe. And in the meantime, I want to copy the fields. So let's copy over the fields. So if I think again about the new universe or the universe object, we need to understand, I've saved this, I'm getting a lot of undefines because I haven't updated the acceleration or the velocity or the position. Here I need to return the updated universe. So that one I know I can fix. At the end of update universe, I need to return my new universe object. For now, though, I'm copying over the fields of current universe into new universe. All right, and this is almost an exercise in getting familiar with just setting fields, at least specifically within Go. So we say, what are the fields of a universe? A universe has two attributes. It has a width and it has a collection of bodies. So it's very tempting to set, say, new universe dot width is equal to current universe dot width, as well as to then just say new universe dot bodies is equal to current universe dot bodies. And consider our job done. This will not work. And it is not clear at all why this won't work yet, but I hope that that will provide some foreshadowing and some interest in kind of taking the next steps into object-oriented programming and seeing what we're going to do next. I want to leave it a mystery for now, I think, so that I don't have to cover a lot more object-oriented programming in Go, which is what we're going to do soon. For now, I'm going to point out that what would happen here is that if I do this equality, I'm going to have the exact same slice. So just as we have seen that when you pass a slice into a function, you get access to the slice itself. So if you change a slice within a function in Go, it will change the underlying data, you will be able to have access to it. So if I have a a slice called A or something, and I pass it into a function and I change the 0th element of A, that changes it outside. That's not the case for, say, simple types of variables where, like an int or a float64 or a string, where if I pass something into a function and change whatever is passed into the function, it has scope that lasts for only that function. The case is different for a slice, where I can pass a slice into a function and it will alter the slice outside of that function. The same type of behavior is going on here. So if I set new universe.bodies equal to current universe.bodies, I will be giving it the same set of bodies. I won't be duplicating anything. All right, so this wouldn't duplicate the bodies. It would give me the same bodies. And so if I were to update new universe of bodies, I would actually be behind the scenes updating current universe.bodies as well. So instead, I need to range over all the bodies and create new ones. Okay, so this becomes a little bit tedious for now, but as I said, it's almost like an exercise in object-oriented programming in Go. So I need to have a range. So let me range over everything in current universe.bodies. Okay, and here I probably should declare the bodies of the new universe. So new universe.bodies is equal to, let's make it be a slice of body objects. And how long does it need to have? It would be tempting to say 5, but let's be a little precise. For an arbitrary function, it should be the length of current universe.bodies. So it should say how many bodies are currently in the universe. We could be even more precise by saying that the number of bodies is equal to the length of current universe.bodies. So we know that this is a slice. How long is it? And now I could kind of substitute in that num_bodies parameter here for the length of the body slice, that is new universe.bodies, and we'd be in good shape there. All right. Now I'm going to create I'm going to range over the current universe.bodies, and I'm going to declare a new object called B. That's a body object. Okay. Everything will be blank. Set the fields of B equal to those of the current body. Okay. And then way down here, so I've declared a new body object. Way down here, I'm going to set new universe.bodies of I, okay, equal to B. So I've declared my body object. I'm going to set this new variable B, the fields of it equal to those of current universe.bodies of I. And then at the end, new universe.bodies of I is going to be equal to this new body object that I created. So it's just a matter of setting all these fields to say b.name is equal to current universe.bodies of I.name. And this is going to be really repetitive here to keep typing this out. So instead of that, I'm going to say, well, maybe we say current body is equal to current universe.bodies of I. And let's set the fields of B. So b.name is equal to current body.name. And now this is a string. So I will copy over, strings are going to get copied. So whatever the string is in current body.name, that string is going to get copied over, and the name field of B is going to get that copy. B.red is equal to current body.red. B.green is equal to current body.green. B.blue is equal to current body.blue, and so on. We need a mass. We need a radius. And I could even call like a copy fields subroutine here that would handle this as a subroutine so that I don't have a slightly shorter function. But for now, I know I'm just setting a collection of fields, so I may as well just type them all out. It'll refresh my memory as to what they are. So we have a name, red, green, and blue. We have a mass and a radius. We had a position. You might wonder, do I need to set each of the corresponding fields here? It actually would be okay since we don't have a slice, but we may as well be as completely precise as we like. I'm going to do the accelerations. Acceleration.x. I'm going to do the same thing for the y component. So set the y components, and then I'm going to set velocity. And this is a hideous function. As I said, there's going to be better ways of writing it, but I'll allow you to kind of think about those after we learn more about object-oriented programming at a future time. So I've set all those fields. Name, red, green, blue, mass, radius, position, velocity, and acceleration. And if we look at our object-oriented programming, we have name, mass, radius, position, velocity, acceleration, red, green, and blue. So we should be fine here. We've got all of those reflected. And then at the end, I update new universe.bodies of I, i.e. the ith body in the universe, equal to b. And all the fields should have been copied successfully at this point. And so new universe, after I've done that ranging over all the bodies, will have all those fields copied over successfully. Now, we can do something more interesting, which is build our physics engine. So to build this physics engine, we need to write our update acceleration, our update velocity, and our update position functions. The meat of this is going to be contained in our update acceleration subroutine. Update velocity and update position will be based off of some Newtonian equations and will proceed quite quickly. So for now, we just need to write update acceleration. Let's focus on that. So you'll remember that to write update acceleration, we need a compute net force subroutine. So I'm going to move this to here. So update acceleration, what does it do? It needs to know all the bodies. So it takes a universe object. I don't have to give it the entire universe. I could just give it the bodies in the universe, as well as, let's do it that way, new universe.bodies. Okay. So it takes in a collection of bodies, slice, and a body object. And what does it do? It computes the acceleration of the body object based on the force of gravity of everything in the universe. Okay. So update acceleration is a function, and it needs to take, let's say, bodies as a slice of body objects, and it needs to take B as a body object. So it's going to say, based off of the force of gravity of everything in that slice, what is it that, what's the net acceleration that is contributed by all of these bodies exerted on B. All right, and so I could also, up here, I've represented update acceleration as taking the bodies, because the width parameter for the universe isn't important. Or I could have just, taken the universe here, current universe, something like that. But I like having access to only what we need. So in that case, I'm going to undo that and say that let's take bodies as a slice of bodies and B as its own body. And what will it produce? It needs to produce an acceleration, which is going to have an x component and a y component. So we're going to have an ordered pair there. What's the acceleration in the x direction? What's the acceleration in the y direction? All right. So in order to write this function, I'm going to create an ordered pair variable. And down here, that's what I'm going to return. So I said I'm going to return an ordered pair. Let's declare it, and then I'll return it. I want a force, which is itself going to be an ordered pair object. So what is the net force that's being exerted by all these bodies on B? So I'm going to take both of those parameters that I've passed into update acceleration, and just as we saw in the pseudocode level, I'm passing them down to a compute net force subroutine, and that will give me the force in the x direction. So what's the magnitude of the pull in the x direction? What's the magnitude of the pull in the y direction? And I'll say, well, once I have that net force, I'm going to set the acceleration in the x direction and the acceleration in the y direction. Well, what should they be? Here's where we apply Newton's second law and say that F is equal to m times a. So if I want a, I'll just divide, and I'll get that a is equal to F over m. So here's where we apply Newton's second law, which is F equal to ma. And so a is equal to F over m. And so this division breaks down over the components too. So I'll be able to say, what's the force in the x direction divided by the mass? And here I'm interested in the acceleration of b. So I need to say, what is b dot mass? And so if b is very small, for example, the same amount of force is going to move it a lot more. If b is very massive, the same force will move it not by very much. So the bigger the force gets, if the mass is held constant, the more the acceleration. Or if I keep the force constant, the bigger the mass, the less the acceleration, since you won't move it as much. So what's the force in the y direction divided by the mass? That's the acceleration in the y direction. So do this over components of the force. Okay? And that will give us the acceleration as an ordered pair. At the end, we're ready to return the acceleration. So I've just passed the work to a compute net force subroutine. I could have done everything within this function too, but I like thinking of it as I need to update the acceleration field. Let me write a separate function to think about this as a force, and then simply do the division based off of Newton's second law. All right. It's also cool. You get to see kind of, actually apply Newton's second law. I love doing it in physics class, but here we see it on a coding level too. So what is it that compute net force does? It's very similar. So we say compute net force takes a slice of bodies and a body object, so a separate body object. It returns the net force of gravity that the bodies exert on the given body. Okay, that's a lot of bodies in that. But we have a compute net force function. We're going to take the bodies slice of bodies, and I'm going to take a separate body. Okay, so this also doesn't necessarily assume that this body is included in the slice, so it's a generic function. What we're going to have is a body that is included in the slice, but for this specific function, we have something that's even more general. And it's going to return the net force of gravity here, and as an ordered pair. Okay, so the ordered pair are going to be the components of that force. What's it getting pulled in the x direction? What's it getting pulled in the y direction? And so that gives us an ordered pair object. Okay, and so here's where we needed a little bit more physics in order to say, well, I need to range over all the bodies, and I need to factor in how much each of those bodies contributes to the force. And so I could have a net force variable, for example, called an ordered pair, or called net force. And that's what I'm going to return. So I'll go ahead and put my return statement in. And in the meantime, I'm going to then range over all the bodies in the slice and compute the force that they exert on the given body. So remember, there are multiple different factors here. There's G, which is the constant, so that's always going to be the same for any two objects in the universe. But then that needs to get multiplied by the masses of each. So the bigger the two bodies is, the greater the force of gravity between them. And then you need to divide by the distance between them squared. Okay? So those are details I could be concerned about right now. Remember, I said on the pseudocode level, nothing quite like just delaying details until the moment that they're needed and just use as many subroutines as we like. So for example, instead, I could range over all the bodies. And rather than worrying about computing the force, I'm just going to call a compute force subroutine. So I could say force is compute the force that bodies of I exerts on the given body B. Okay, so what is it that the ith body in the universe contributes to B? You could even get fancy here and say, well, I only want to do this if bodies of I is not equal to B. All right, so I only want to actually do this computation if I hit something that's different. All right, I don't need to compute the force that a body exerts upon itself. Since hopefully that would be 0. And so after I compute the this force that bodies of I exerts upon B, or that they exert upon each other, given that this force is equal by Newton's third law, we then say, well, let's add to the x component of this net force, whatever it is. So add the contribution of force to net force. And just like with everything else, we're going to do this over the x component and the y component. So we say net force.x plus equals force.x, and net force.y plus equals force.y. So after we've done that, we're going to hit return net force, since we've ranged over all the bodies, and we've added their contribution to the net force variable. All right. So now we're one level simpler. And so we're going to say we know what compute force needs to do. So compute force now, we're at the point where we take two bodies, and it computes the force exerted due to gravity on the second object due to the first. Okay, so we're going to need a function called compute force that takes I'm going to do B2 and B as bodies. So B2 is the kind of external body. Notice that's how I've written this here. You might think about it the other way around. That would allow me to do a B and a B2. But I like taking the collection of bodies and thinking about the order of the parameters in this way. So based off of the given collection of bodies, what is it that this given collection exerts on B, and keep this consistent. So how much force, or what force, does the ith body in this slice exert on B? So we have a compute force function here, and it's going to need to return an ordered pair. And we saw two ways of writing our compute force function. One way would have to figure out what's the angle, that if you look at B2 and B, what's the angle that B2 is with respect to B. So we could have a magnitude of a force, and we need to know the angle as well. And so we have to have this conversion from polar coordinates, and things would get a little messy with a few subroutines. By computing the angle, we'd have to do some trigonometry, and it would get a little bit messy. So we had a simpler way of computing this force. And the way that we had before was to say, let's declare a force variable as an ordered pair. Okay, and force.x and force.y get the default values for floats, which are 0 and 0. So if you declare an object, it has two float fields, then the floats are going to get the default values automatically. So let me find the distance between B2 and B. All right. So this is going to tell me how far apart they are. And now once I know how far apart they are, I'll apply the formula for the magnitude of the force. So the magnitude of the force, I'm going to use capital F for this, is equal to G. So that's the constant that we have in main.go. Right, I've declared a constant. We haven't worked much with constants, but we can have this global constant that's accessible to everyone. It's outside of any function. It's outside of a func main. It's outside of a type declaration. It's never going to change, so we're not going to be able to update it later. I'm just declaring it in one place. So instead of it being a variable, it's going to be a constant equal to its value. And I'm going to use that now. It's only going to occur in one place, which is in this compute force function. I'm going to use it to say it's G times, well, it's the mass of B2 times the mass of B divided by the distance squared. Okay? And that's just the gravitational force equation. All right. Once I have the magnitude of the force, here's where we said, well, how far away, what is the, how far away in terms of x coordinates and how far away in terms of y coordinates is B2 from B? Because that's going to influence kind of what's the force's x component and what's the force's y component. The bit farther apart they are in terms of x, and the farther apart they are in terms of y, this will make a difference. And so I'll say, well, I can know how far apart they are in terms of x coordinates if I take the position of x, of B2 in the x direction, and what's the coordinate of B's position. Okay, and so that will give me, if I'm B and B2 could be anywhere, that will give me the difference in the x values here. And delta y is going to have the difference in the position y components or y coordinates. Right? And here's where we're going to update the x and y components of the force variable that we've declared that we're eventually going to return. So now we set the x and y components of force. And the way that we did that on the pseudocode level was to say it is equal to the magnitude of the force times, and what we wanted was f times the cosine of the angle. So the cosine of the angle at which B2 lies compared to B. Okay, and force.y was going to be equal to f times the sine of this angle. All right, and I'm going to avoid having to do this because I had shown in the pseudocode lecture, or the theory lecture, that I can get this cosine for free because it's just delta x over d. Right, and the sine of that angle I get for free because it's just delta y over d. All right, and so I've set the x and y components of the force, and I will return that force object. And so you see we have quite a lot of top-down here, right? So we have the simulate gravity, calls an update universe. Update universe calls an update acceleration. Update acceleration computes the net force that all the bodies in the universe, it could be a few, it could be many, or it could be millions, exert on a single body. And that compute net force ranges over all those bodies and computes the individual forces. And so we have the compute force subroutine here, which is where the details lie. All right. We even have one final little subroutine, which is a distance. So I need to know how far apart two things are. But in this case, I could just write the distance function. And if I wanted to be very precise, I wouldn't even take in the bodies themselves. I would take their positions. I don't need to know anything else about them. So why not just give the distance function exactly what it needs to know, which is where these two things are. So distance takes two position ordered pairs, and it returns the distance between these 2 points in 2D space. So we have a distance formula function. It's going to return a float 64, and it needs to know, let's say, P1 and P2 is ordered pairs. So each of these is just going to have an X and a Y coordinate or field. And so how is it that we do this? This is the distance formula from days of pre-calculus long ago. Okay, and now we get to see it on the level of Go. So the distance formula says if you have 2 points, you have X and Y coordinates, well, you take the change in the X values and square it. You take the change in the Y values and square it. And then you take the square root of those sums, since it's just the hypotenuse of this right triangle with legs delta X and delta Y. So I'm going to have, I could have already set this distance, since I've already set delta X and delta Y here. But I like calling it out as a subroutine, keeping everything nice and modular. It'll be easier for testing and so on. Have a nice simple function here where I say it's P1.x minus P2.x, and then we have a delta Y, which is P1.y minus P2.y. So I have two ordered pairs. They each have an X coordinate and a Y component. I take delta X and delta Y, and here's where I need to return the square root of delta X squared plus delta Y squared. All right, and so that's delta Y squared, this is delta X squared, and if I take the square root of the sum of those, I'm going to get the distance between P1 and P2. All right, so I've written now that very lowest level subroutine, which is distance, and I still haven't defined update velocity or update position. I also need to define the math package, so I'm going to scroll up and import the math package. That will handle that. And in the meantime, I've got update velocity and update position undefined, so that's where I'm getting these comments back. I haven't written those yet. And so fortunately, this is where I just apply some much simpler formulas for updating a velocity and position of an object after a given amount of time. So from dynamics, I'm going to have a function called update velocity that's going to take, I'll remind you that it takes the body that we're interested in. So this is where we're setting the velocity of my body object based off of a given time interval. And so update velocity is going to need to know a body object and the time interval as a float 64. So update velocity takes a body object and a time interval in seconds. It updates the velocity of that object over the time interval using kind of Newtonian dynamics equations. Okay, that's a mouthful, but in other words, it's going to return an ordered pair corresponding to the updated velocity. So if you see how it's used, I'm setting the ith body's velocity equal to updating the velocity of that body over the time interval. And so the formula here is that the velocity over the time t is equal to, well, it's the, so if I say var v ordered pair, I'm going to return v, and I'm going to set v dot x and v dot y. So here I'm going to say v dot x is equal to whatever the body's velocity is in the x direction. So b dot velocity dot x to indicate its x component. So whatever its kind of initial velocity is, which got copied over from the previous universe. And I'm going to add to that b dot acceleration in the x direction times the time interval. Okay, so we have this will be in meters per second. Acceleration will be in meters per second squared, and we multiply by seconds, so it cancels out to be meters per second. So acceleration over multiplied over a time gives us a velocity. So if I'm really getting pulled very hard in one direction, but I'm going to get pulled for a significant amount of time, and after that amount of time, I'm going to be going that much faster in that direction. So the higher the time, the higher the velocity in that direction. And the same thing in the y direction. I start with whatever my initial velocity is. So I may be headed in this direction or headed in the negative y direction, but I'm getting pulled in the positive y direction. And so I'm going to multiply the y component of the acceleration of b over the time. Okay? And I will return v. Update position is going to be a very similar function. It takes a body, it takes a time interval, it returns an ordered pair. It's going to need to declare an ordered pair object. That's going to be our position. It will return that at the end. And in the meantime, it needs to apply the standard equations here. And the standard equations here are that p dot x is equal to wherever p started, whatever the initial position was. So that's the position in the x coordinate of the position of the current body. So this is where b currently is. And then to that, I'm going to add whatever my current velocity is. So I'm going to take, if I'm headed in a given x direction, I'm going to multiply that over the time, since that's how much my position will change. If I'm going, time is 1 second, and I'm traveling at 30 meters per second. Well, I need to update my position by 30. Okay, so here it's going to be, if I'm traveling for 2 seconds, I would update it by 60 and so on. So it's b dot velocity dot x times the time. And the same thing for the position of y. So I have b dot position dot y plus the velocity of y times the time, and then each have an additional term which corresponds to the acceleration. So if I'm also accelerating, I don't just have a given position and a given velocity, so I'm traveling, and remember we're going to have moons that are orbiting. So I don't just have a given position and I'm traveling in a certain direction. My position will actually bend based off of the acceleration. So that's going to have an additional factor here. And so it's 1/2, the equation says that it's 1/2 times the acceleration in whichever direction times, and in this case, it's the time squared. Okay. And so here it's the acceleration in the y direction times the time squared. And that's it. We've built our gravity simulator because we've produced our update acceleration, update velocity, and update position functions. And that was all after we created after we had our copy universe function. That's all we needed. I could copy over function comment for update velocity. Just to be completely precise, what is it that this does? It takes a body object and time interval. It updates the position of that object over the time interval using these Newtonian dynamics equations. Okay, so here's where I get to. We've used a little bit of high school pre-calculus, a little bit of high school physics, and we're going to build this out into a simulator. So all of the functions in gravity.go are good to go. Now it just remains to produce our simulation, and I should be okay, I think, to compile this and see that everything compiles, which is what I had seen in Atom, which is good. Now it's just a matter of running the simulation and visualizing it. So one thing that I could do, I guess, would be to go to main and just, hope that everything is going to be okay with my simulation. I'm not going to be able to see it, but I can at least run the simulation. So remember, I handled everything in main for us and declared all our variables and all the fields of the variables. And so we have a Jupiter system that's a universe object. It has a given width, 4 billion meters. It has a given set of bodies whose masses and colors and so on have been declared. And so we're ready to implement our gravity simulator. And we should say, all right, well, what is the highest level function? The highest level function is going to take an initial universe, which was in our case is called Jupiter system. It's going to take a number of generations as an integer, and it's going to take a time interval. All right, so maybe I should here, let's read in some command line arguments. Okay, so maybe the command line arguments that I would read in would be, I'm going to set Jupiter system behind the scenes, but maybe a number of generations and a time. So let me say that numgens is os.args of 1 and time is os.args of 2. So if I pass in command line arguments, the os.args of 0 is going to be the name of the program, but os.args of 1 is the first thing that's typed in, os.args of 2 is the second thing that's typed in. And so let's set numgens equal to what happens if I try to string convert to an integer of os.args of 1. So let's read in some command line arguments. So I'm going to try and do this conversion. I make it an error. So if I try to pass in, I don't know, something that's not an integer, 43.4, or the string hello, that would be bad. So I want to say if there was any error in that process, let's panic and say that there was an error problem reading first command line argument. And otherwise, everything is going to be okay. And so time is going to be os.args of 2. In this case, time is going to be a float. So time error 2 is going to be string convert dot parse float. Okay, and it's going to take, I'm going to have a float 64. So I'm going to parse out os.args of 2 as a float 64. I can say more about why this is 64 bits later when we do a little bit more deeper programming. But for now, I'm just going to say if you want to float 64, you can call string convert dot parse this float of whatever you want to parse out. So here it's os.args of 2, the second command line argument, and then 64 will make it a float 64. And if error 2 was not nil, then we're going to have a problem reading, I'll say number of generations argument and time argument. Okay, so I need to have my OS and string convert packages, so I'm going to add those to my declarations. And that should handle everything. I haven't used numgens or time, but that's all right, because I'm ready to implement the gravity simulator. So I have Jupiter system, I have my number of generations, and I have my time interval. So I'm going to say, let's call it time points is equal to animate system. Is that what I called it? I called it simulate gravity, even better. So let's simulate gravity of initial universe here is called Jupiter system. The next parameter is number of gens. And then we have our time interval float 64 as well. So that I have not used yet, but I could say simulation run successfully. And at this point, I haven't actually used time points. So for now, I'm just going to say underscore equals simulate gravity, or I don't even need to return anything. Go will be fine if I call a function and I don't want it to return anything. I'm just going to call that function, which is something that we saw before when we timed functions. So let's see if our simulation runs all right. So I'm going to go build. And now I'm going to pass into Jupiter. I'm going to run Jupiter, which is the name of my folder. So I've created an executable file here called Jupiter. And I'm going to give it the command line arguments. So number of generations, let's do this for 100 generations where 60 seconds is the time interval. And we're going to hope that everything goes okay. And allegedly the simulation was run successfully. So we'll see if that was the case. We may have some horrible bug, but we at least didn't hit some dreaded runtime error like a slice out of bounds or can't access a certain field or anything like that. So at least hopefully we should be in good shape. And we can actually see the result of what it is that we did. So that's part 2 here, which is much shorter than what part 1 was. But we're going to, now that we've got the main.go written and we've got the gravity simulation functions written, it's just a matter of drawing these. I already wrote some function signature comments here, high-level comments for each of the functions. And so we have an animate system function. It's going to take a collection of universe objects, I should say slice of universe objects, along with a canvas width parameter. So function animate system is going to take, I keep calling it time points, or universes might be possible, a slice of universe objects, and I'm going to take a canvas width as a float 64, since that was the, excuse me, I need an integer because it's going to be the number of pixels. It's not the width of the universe, it's going to be the number of pixels. And it's going to generate a slice of images corresponding to drawing each of the universes. All right. So the image object is going to come from the image package. So I have a slice of images. So they're called image.image, meaning that they come from the image package. So I should import image. And the image type is just a capital I image. Okay. So the hard part here, why this, what will make this tricky is that we have a, when we draw the object, if we're worried about the most complicated detail first, I may have a universe that is 4 billion meters wide, or if I did the solar system, it would be even bigger. But I want to draw it on a small canvas. And so I need to do a scaling of that huge universe down to a canvas that may be 500 pixels by 500 pixels. That winds up just being algebra. And it's another example of, I want to worry about it right now so badly. But instead, why don't I just make a slice of images of length what? Well, length of time points. And that's what I'm going to return down here. And in the meantime, I'm going to range over all the time points. And I'm going to set images of I is equal to, let's draw to canvas, okay? What is it needs to know? It needs to know time points of I, and it needs to know the canvas width. So I'm going to pass this to a subroutine that's going to take a single universe and a canvas width and deal with the fact that the universe is going to be, probably bigger, not necessarily, I guess, but probably bigger than the canvas width that we have, and handle this. So that's why I've already got draw to canvas here. It's going to draw an image onto the canvas. It's going to be a square canvas, so the universe has a width in meters, but the canvas has a width that's going to be canvas width pixels by canvas width pixels. So I need a function called draw to canvas that takes a universe object. Okay, time points of I is just a universe. So I could call it U. And it takes a canvas width integer. Okay, because pixels is, a pixel is a square on your screen, so that's always going to be an integer if we're looking at it as pixels by pixels. And it's going to return an image.image. Okay, so remember, images of I is getting set. What was images? It was a slice of image objects. And so images of I is going to be equal to an image object. So draw to canvas needs to return an image object. All right. We don't know anything about an image object, so that's going to seem concerning for right now, but I'm going to point out that that's what we're going to pull from the canvas package that we've already imported. So, or that we've already installed, I should say. I haven't imported it yet. So let's do that. I've provided previously some kind of a tutorial on drawing things with canvas. But we can set a new canvas. And there's a function called create new canvas that takes the number of pixels that we want it to be wide and the number of pixels that we want it to be tall. Those are the two parameters into this create new canvas function. If you look at canvas.go, you have a create new canvas. It takes a width and a height in pixels, and it produces a canvas object. So it does everything behind the scenes for us, and it returns the canvas object that we need. Some of this notation will be a little confusing perhaps for now, but that's okay. I'll explain. You'll understand soon when we do more object-oriented programming that there's a little more to object-oriented programming that we need to handle, but that's okay. I want you to think for now, this is, if we can understand this on a high level as taking the number of pixels wide and tall it will produce a canvas object. What is a canvas object? You can look and see, well, canvas object has, this is going to be a pen that will, think of this as a pen object that will do the drawing. It will produce an image, so if we want to actually see the canvas, then we're going to need an image, and so that's going to pull everything from the image package, so everything's going to be done more or less for us there in terms of how that image object is declared and what its fields are, and so you can understand that we can really get into a rabbit hole here with the object-oriented programming. But for now, I'm just going to think of the canvas as having these four attributes. I'm going to have a pen that's going to allow me to do the drawing. I'm going to have an image object as another field, and then width and height are measured in pixels. All right. So again, a pixel is a square on a display, or the width of that. Okay. So that's the canvas object. If I call create new canvas, it will give me a canvas where I have a pen, I have an image, and it has the appropriate width and height. I'm going to create everything as a square. So for the universe, as opposed to having to deal with rectangles, I'm just going to assume a square universe here. Remember I said it only has one field. It has the width in addition to the bodies. So a universe just has a width, so I'm going to assume it's the same wide as it is tall. So I'm going to give it the canvas width and create the square canvas. All right. And there's just one quirk here, which is canvas.go is not contained within the Jupyter folder that I provided. It's separate. We've installed Canvas as its own package. So if I want to grab create new canvas, I need to go to this installed package that we've created, that we've installed, and I need to import it in the drawing.go at the top of the file. And create new canvas comes from Canvas, the Canvas package, so I need to call it just as I would call fmt.println, just as I would call rand.nn, just as I would call os.args. It comes from the Canvas package, so I need to call it after importing that package. So now I'm going to have canvas.createNewCanvas based off of it being that number of pixels wide and tall. Let me create a black background. So I'm going to set the fill color, and black is, if I want to make a color, black corresponds to not adding any light. So complete absence of red, green, and blue light will give me black. So if I set all those values to 0, I'll have a black fill color. I'm going to set a rectangle. So this notation will also be something that you're not familiar with yet in terms of how it works with object-oriented programming. You're telling me that I have an object called C, that's a canvas. Okay, so C is our canvas object. But I have a C dot set fill color. So let me hold off on explaining that until we do a second part of object-oriented programming. But for now, I just point out this is how we can kind of draw on the canvas. So if I create a clear rect and I go from the x and y coordinates of 0, 0, to canvas width and canvas width, that's going to draw a black background across the entire canvas. Okay. And if I call c.fill, that will fill in that rectangle for me. One little thing I believe that I've missed is here with make color. This is another function that comes from the Canvas package, so I should call it using the Canvas package. So it's going to be canvas.makeColor of 0, 0, 0. These other function calls are going to be okay though. All right. So we're going to set the fill color, make the color as black. So set the fill color to black. Create a rectangle from 0, 0 up to canvas width, so that'll fill the entire canvas, and then fill that. All right. And now I'm going to range over the bodies. So I have a universe object U, and I'm going to range over all the bodies. Notice I've got this two variable or two variable declaration here for ranging over the bodies. So I'm going to have the index I when I range over the bodies, and I'm also going to have the body itself because that'll be helpful. All right. So I'm going to range over all the bodies and draw them. And I'm going to set the fill color equal to canvas.makeColor of whatever my body is colored. So remember, the body has b.red, b.green, and b.blue. Those are its color attributes. If you look at Canvas, you will see this in Make Color. You're going to see R, G, and B as uint8s. Those are the field types of the colors, red, green, and blue for a body. And it's going to return a color object from the color package, so color package, color object. And then it will kind of produce that color object for us. And that color object is what is taken by this set fill color function. Okay. So we'll set the fill color equal to the appropriate colors for B, b.red, b.green, and b.blue. And if we're in the center, then we're at Jupyter. Okay, so if we're at the 0th body, that's Jupyter in this case. And actually, let me hold off on this. I'm getting a little ahead of myself, so I don't want to distinguish Jupiter just yet. So we're going to say, actually, there's no sense in spoiling this or trying to set this up as a surprise. What's going to happen is for most values that we're gonna do, for most values of the canvas width, the moons are so much smaller than Jupiter, and you're dealing with a system that's so far out, that's so sparse, that each of the moons would take up less than 1 pixel. So for that reason, you would try to draw them, but they would be so small you wouldn't actually produce a single pixel for them. And so what I'm going to do is I am going to draw a circle for Jupiter that's the appropriate size. So this code won't be completely general. You may want to adapt it a bit if you're dealing with a system where everything is visible, but I'm going to multiply the sizes or the radiuses in terms of how they're drawn of all the moons or all the orbiting bodies by 10. And so I am going to say we're going to create a circle for Jupiter, and we need to know, so c.circle, if we look at Canvas, and I don't want to, this isn't, the point of this is not to be a drawing tutorial, but if I look at circle, how circle works is that it needs to know the center x coordinate, the center y coordinate, and the radius that we're interested in. And so it's going to produce this circle centered at xy with radius r. So I could set cx is equal to something, cy is equal to something, and r is equal to something. And then I'm going to set cx, cy, and r. And here's where we need to do our scaling. So it's just some algebra that we need to handle. So we say it's the position of B in the x direction, integer divide by the width of the universe. Okay, so that will scale it down. That gives me kind of, if the width is 4 billion and the position of a body is at 1 billion in the x direction, then I'm 1/4 the way over in the canvas. So I need to take that 1/4 the way over in the canvas, and then I'm going to multiply it by the canvas width. So I'm 1/4 of the way over in the canvas, but then the canvas has 1,000 pixels, for example. Then I need to go and I need to set cx equal to 250. So this will give me the fraction that I'm over on the canvas in the x direction, and then I'm going to multiply that by the width of the total canvas. So, I've done this scaling of where I need to draw on the canvas corresponding to the universe, all right? And then it's the same thing for b.position.y divided by the width of the universe. And here, I said integer divide, but it's certainly not an integer division because I'm getting a fraction, all right? So I have the position of y, maybe y is 70% up on the canvas, or in the universe. And so if that's the case, then I multiply it by float 64 of the width of the canvas. All right. And so that's the center x and y coordinate of the circle that I want to draw. How wide should the circle be? Well, in this case, it's just going to be b dot radius, so that's a float 64. I'm going to divide it over the width of the universe, so that tells me kind of what's my scaling down, and then that scaling down will then get scaled back up based off of how big the canvas is. All right, and then I'm going to draw my circle. So everything will proceed naturally for Jupiter. I scale it down x, y, and r, and then I multiply by the canvas width. Else, moons need to be scaled up. So the x and y won't change, but the moons need to have radius scaled by a factor of 10 to be visible. Okay, so I'm going to get a little clever here, and I'm going to declare cx and cy outside here, since they're not going to change. And r otherwise is going to be declared here. And in fact, I could do the same thing and have R declared outside there. And if I scale the radius by a factor of 10, I'm going to scale the radius by a factor of 10 there. So I'm going to multiply it by 10, and then I'm going to draw the circle there. So it has the same center position, X and Y, but R is going to need to be a little bit bigger so it's actually visible. Okay. And then at the end of this, I'm going to call C.fill to actually fill the circle. And again, as I've said, you may have different systems where you need to scale by a bigger factor. You can adjust this as per needed. You could perhaps try to detect that and scale things accordingly. And so now we're going to be ready to return what it is that we want to return. So what do we return? We want to return an image object, all right? And so I've created a canvas object, and I've filled in all the values there. So I've made a black background for space, and I've filled in all the circles based off of the current positions of the bodies. So it's just a matter of, we want to return an image, not a canvas. But if you remember, I pointed out, what is the canvas object? The canvas object, sorry, this will make you maybe dizzy, but canvas object has 4 fields. One of them is called img, and its type is an image.image object. So we would love to say, I want to return c.image. After all, that's the field corresponding to the canvas C. That is the image of the canvas. And then we'd be done, right? Because we've returned this image.image. And that's draw to canvas. It's actually done the drawing. And then that's iterated over all the time points, so all the universe objects that we have in the Animate System function. And so we really just have these 2 functions here, and we'd be good to go. Just one problem, all right? We get this, I could compile and show the same thing. We get this compiler error when we compile that says c.image undefined, cannot refer to an unexported field or method image. And the question becomes why this happens. And the problem here is that the image object, or the canvas object, so every time you'll notice, every time we have a function throughout this canvas file, the function always starts with a capital letter. You also have these fields, and they all start with lowercase letters. When you start to install packages and then you want to import a package, in Go, if a field starts with a lowercase letter, you won't be able to access that field outside of the package. I can access it inside the package, but you might imagine this might be a helpful security feature, or to allow to present something to a user where some of the time we want to have access to things, other things we don't need access over. And so we will not be able to access from within drawing c.image. I can access it within Canvas. Within canvas.go, I can access the image field of the canvas object, but I won't be able to access it from outside of the package. The same goes for if I made a function, for example, if I had the canvas.makeColor and I were to change make color so that this were a lowercase m, and then I reinstalled the package or so on. That makes it private to the canvas.go file. So everything within this file can call make color as much as it likes, but I couldn't call make color from outside of the package. Here I want to be able to do that. I don't want to actually change img here. I could change it to be capital I. I'd have to change it throughout canvas.go, and then I'd have to change it in Gif Helper or in drawing.go. I would need to change the appropriate line here to c.capital I, and then everything would be okay. I don't like that so much, so instead I'm going to have a function called getImage, all right? And so I will take a canvas object, and I will return an image.image object, and it's inside of canvas.go. So now it will be okay for me to say return c.img. Keep that as a lowercase, all right, and not be accessing the fields of this object from outside of the package, but I have a getImage function that will give it to me. And notice this has a capital letter, which is what we're going to allow, what will allow us to call getImage from outside. And so instead of return c.image, I'm going to return getImage of c. And that should be okay. So that now if I save, it will say undefined getImage because I need to pull it from canvas. And now when I save, I'll probably get an issue because I should go back up in my navigation to SRC and then navigate into Canvas. And let me install that package again. So everything is precompiled behind the scenes. And now I'm going to go back up to SRC, back into Jupyter, and compile this. And I have compilable code. So I have a main.go where everything has been written. Gravity.go handles all the functions. And drawing.go has managed to produce these drawing functions. If you look, draw to canvas is the engine here, but Animate System will take a slice of universe objects, take a canvas width parameter as an integer, and produce a slice of images. So now I'll actually be able to see what I've done. I want to be able to go into main.go and call Animate System. So I have simulated gravity. I want to store the result in time points, which is our slice of images. The simulation has been run successfully. Okay, so now I need to call Animate System on time points with a given canvas width. All right, and now maybe let's take in a different parameter. So canvas width error 3 is equal to string convert. So let's assume this is os.args of 3 is the canvas width in pixels. So it's going to be an integer. And I'm going to convert os.args of 3. And if error 3 is not nil, then there was a problem and I should panic and say that there was an error, problem reading canvas width argument. And so now that parameter has been read in, and I'm going to animate the system, and that is going to produce what? Well, if we look at Animate System, remember it produces a slice of image.image objects, and so I should have images equals Animate System of the time points, which happened when I simulated the gravity on the Jupyter system for the number of generations and the time interval. And so I'm going to animate this system over given a canvas width parameter. All right. So now I can say, well, images drawn. And what's the last thing that we want to do? We want to produce an animated GIF and then exit normally. So in GIF Helper, here's another package that we've installed that will take a slice of image.image objects and a file name and write based off of the images that we have to that file name and produce an animated GIF. All right, and here's where we're using some rendering code that we're borrowing from GitHub and so on. And we just want to apply it by thinking about this on a high level as a function that takes the images and the file name. I could pass in file name as another, excuse me, I need to go to main. I could pass in file name as another parameter, but here for now, we're just simulating Jupyter, so I could allow you to produce a more general piece of code later. For now, I'll just say file name is Jupyter, moons, something like that. And so if I want to call this, I need to say images to GIF. And remember, I've installed GIF Helper. So I've installed the GIF Helper package, and so I should call GIF Helper dot images to GIF. Notice it's a capital I, so we will have access to it. GIF Helper dot images to, it was there briefly, images to GIF, and here it's going to take the images that we produced, this list of images, and it's going to need to know the file name that we're giving it. So the file name for the GIF, and that will produce the animated GIF, and at this point we will be able to exit normally. So it says GIF Helper is undefined. That's okay. I forgot to import it since we've installed it, and now we should be able to import it. So now if I compile, I shouldn't have any compiler errors, and I will be running this simulation with a time interval of whatever I give it. Okay, and so remember that os.args of 1 is the number of generations. So I have something that I can run. So I'm going to run Jupiter. os.args of 1 is equal to the number of generations, so let's just do a simple run, 100 generations, 60 seconds at a time, and then os.args of 3 is the canvas width, so maybe 500, something like that. We hit enter. And so the simulation happens very quickly. The images are rendered quite quickly, and we can see, what's taking this a little bit of time to finish. Well, in this case, it's the drawing to GIF. So calling GIF Helper and using kind of some existing code, this animated GIF rendering is taking a little bit of time. It's a little bit more on my computer probably than it would be otherwise, since I'm streaming as well. So we have a couple of concurrent processes that the computer is trying to handle. And I'll say more about that when we get to parallel programming, but in the meantime I'm just waiting for this to produce an animated GIF. Everything has exited normally, and so we should be able to take a look at what we've done. Now let's hope that things don't fly off into space. I'll create a new window of Safari. So I've got a new window of Safari, and I'm going to put it here, and we should be able to see our simulation. And I've got to say, it doesn't look like much. All right, and so this will be the final stage of what we do. You can see that it will jerk back at the end. So we've done this for 100 generations. So 100 minutes, which is a little over, almost 2 hours. So you might be surprised that you would see anything if the gravity simulation has been done correctly, right? If you look at the moons of Jupiter, I mean, if you look at our own moon, it takes 28 days for the moon to make a revolution around the Earth. So have we done something wrong? And in fact, if you look at the orbital periods, or how long it takes the moons of Jupiter to go around Jupiter once, to revolve once, it's much, for these 4 moons, it's much less than it is for our own moon. So this moon that's the closest one in is, this one is Io, okay? And so if we look at Io's orbital period, then it's only 42 hours. So in less than 2 days, Io will make a complete rotation of Jupiter. And 2 days is 48 hours. So from that perspective, it's actually not shocking that we see a little bit of movement here. If we take a minute as our step, so 60 seconds, and then we look at 100 minutes, we're going to wind up at almost 2 hours. So in 2 hours, we will see Io move a little bit. The problem is that took us a while to run. I mean, it took us 10 seconds or so to draw the GIF here. But it shows an important part of programming, which is to there's nothing wrong with giving feedback. And on a higher level, there's nothing wrong with timing certain parts of our program to see what is it that's quick and what is it that's slow. In this case, running the actual gravity simulation is very, very fast. You know, when I ran this simulation run successfully, almost instantaneous, you know, from the perspective of the human eye, practically instantaneous. The images were drawn in less than a second, and it's the GIF that takes the time here. So here's where we say, okay, we're waiting on a GIF where we're watching these moons just very, very slowly revolve around Jupiter. Instead, why don't we just, you know, and one knee-jerk reaction would be to take a much bigger time step. So instead of taking an entire 1 minute, we could take an hour, something like that. And I'll let this run, and we'll look at what happens when I go from 60 seconds to 3,600 seconds. And I'll pause. So what's nice about opening a GIF in Safari is that as soon as this finishes, I'm just going to refresh the page and we'll see the simulation, or the GIF hopefully. So it exited normally. And let's see what happens here. Oh no, an Io collided with Jupiter and then flew off. So we get these tight orbits, and then so the moons kind of get sucked into Jupiter and then spun out and tossed out. And this is probably not what is about to happen for the moons of Jupiter, right? If it is, then we need to alert NASA immediately. What's probably happening is what I mentioned long ago, which is that if we use a small value of the time parameter, we'll get a very accurate simulation, although it might take us longer. And the bigger the value that we use, we're going to start seeing the inaccuracies compound. So if I'm off by a little here and Jupiter sucks it a little bit too close to itself, you know, we were traveling in this direction and I should have moved it just a little bit if we were making small time increments, but instead I moved it a lot, then it's going to wind up drawing it tighter and tighter into itself, and that's an inaccurate simulation. And so students will often think, oh no, what do I have to do? I now have to just run this for like thousands of generations with say a small 60-second time interval. You say, no, not necessarily, because actually generating the universes doesn't cost us much computationally in terms of runtime. What takes us the time is drawing the animated GIF. So let me add one more parameter and then we're going to be done. I'm going to add one more parameter, and that parameter is that I only want to draw the image every so often. So instead of drawing it for every single time point, why don't I draw it every 100 or every 200? Or better yet, why don't I just take that as a parameter from the user? So why don't I, in os.args of 4, is number of generations to go before is, I should say, the frequency number of generations with which we draw images, universes to images. Here we're entering kind of the end of the second hour of me programming, so I'm getting a little sloppy, I guess. But so if I give, say, frequency error 4 is, let's string convert this from the user, os.args of 4. All right, and if there's any problem with that, I want to check if error 4 is non-nil. I'm going to panic and say, well, there was an error reading the frequency argument. All right, and I haven't used that, so I want to use it. And I'm not, this has nothing to do with the simulate gravity function. Everything here is going to be the same. I'm still going to produce functions, time points. But now when I animate the system and I draw the images, here's where I want to pass in this frequency parameter. All right, and so the animated GIF will only look at the images that I've drawn. All right, so I want to draw the very first one, and then if frequency is 100, I want to draw 101 and 201 and 301. Or if I'm zero-based indexing, I want to draw images. I want to draw time points of 0. I want to draw time points of 100. I want to draw time points of 200, and so on. So in general, I want to draw time points of 0 times frequency, 1 times frequency, 2 times frequency, 3 times frequency, and so on. And that will give me a completely general piece of code where I have yet another parameter. And so I need to go into drawing, and I need to give it a frequency integer. And in the interest of time, I'm not going to update my function. Well, I may as well, since I'm going to publish this. Okay, so it's going to take a canvas width parameter and a frequency parameter, and generates a slice of images corresponding to drawing each universe every frequency generations on a canvas width by canvas width canvas. There's certainly much better function comments than that. But how is it this will work? I said I want to do 0 times frequency, 1 times frequency, 2 times frequency, and so on. So I'm no longer ranging over the time points. All right. I am now ranging over everything up to and including something. So I'm going to go, well, I only want to do this if you think, well, what is it that 0, 100, 200, 300 have in common? They're all divisible by 100. The frequency was 100. If the frequency was 400, I would be at 0, 400, 800, 1600, or 1200, 1600, and so on. So perhaps I only do this if I% frequency is equal to 0. So if the remainder when I divide by the frequency is equal to 0, that's the point at which I want to set images. But this is actually a little trickier because I could compute this algebraically, but I don't need to set images of I. Otherwise, I'm going to have a bunch of blank images. I want to set the next one. So 2 images I want to append what happens when I draw to canvas. Okay, and when I make my slice of images, I'm going to have it be length 0. And now I'm going to only append if the index of the time points universe slice is divisible by frequency. So that's the remainder is equal to 0 when I divide by frequency. And now I'm going to do an append. I'm not a fan of setting the length equal to 0 and then doing all this appending. I will leave that to you as an exercise as to how we can do this with knowing the length of the images slice in advance and then setting images of something equal to draw to canvas. All right, but for now this will work. I just need to save this, and I need to recompile my code because Animate System changed. I don't have enough arguments in the call to Animate System because I didn't save it for one. So I need to save that. So I've passed the frequency parameter into Animate System. And now the code compiles. I need to run. I'm going to keep hitting up until I see. I'm going to run Jupyter. So here we said 100 generations. I'm going to change this now back to 60 seconds, which is the time interval. That was os.args of 2. os.args of 3 was the canvas width, so 500 pixels is fine. And now, instead of 100 steps, let's do, say, I don't know, 2,000 steps. And I'm only going to draw every 20th one. Even in the interest of time, I could draw every 50th one. And let's see what happens. So the simulation was run quickly. The images were drawn quickly. The simulation was run for 2,000 generations, but the simulation happened still very, very quickly. So I'm just waiting on the images to be drawn, or the images drawn and the animated GIF to be produced. And now we'll go back to Safari or our browser, reload the page. And now we see what looks to be a pretty normal gravity simulator. And we can call our work here complete. I could animate this over a larger number of generations, and you'll see that the orbits tend to stay circular. So there may be a very, very slight round-off error because we're taking an approximation of every 60 seconds. So we could get even tighter if we got it down to a second or a fraction of a second. I could do that, for example, if I ran this for, I multiply 2,000 by 60, and I get something like that, and I do it every second. Okay. The simulation still runs very, very quickly. That's 120,000 steps, number of generations, which is really good. You see why it's called Go. Unfortunately, I forgot to also update this parameter. So I would need, the frequency parameter needs to get multiplied by 60. So I need to multiply whenever I had 50 by 60, which gives us 3,000. And so now the animated GIF should be drawn soon. And then I'll refresh the page and make one more remark, or a couple more remarks, and then we'll be finished. So if I reload this, I ran 120,000 generations. It was lightning fast. And I produced the simulation where we can see these circular orbits, where the velocity and positions are just getting updated based off of the force of gravity that these exert on each other. I would say try something wacky. Let me know something cool that you do with this. You could go a lot of different directions here. You could produce a solar system simulator. You could look at different moons, say the moons of Neptune. You could generalize this into three directions, or 3 dimensions. If you have orbits that are in different kind of planes, and then perhaps look at a projection of those. So look at it from one angle and draw it that way. So many directions to go. I'll show one more that we could do here. Remember, I declared the constant g. And why don't I say take the force of gravity and have it. So all of a sudden, the force of gravity gets halved. What's going to happen to our simulation? And so I need to recompile. So go build, and then a lot of computational resources are getting used if the compile step takes that long. But I will run this one, say, let's do it for even more. I'm going to do it for 5 seconds this time. And wait and see what happens. So gravity all of a sudden gets half as strong. Animated GIF got produced. So now everything just kind of floats out into space because gravity isn't strong enough to hold these moons in their orbits. We could change this instead by saying what happens if you multiply the force of gravity by 2, or even let's multiply it by 1.4 or something and see what happens if I need to recompile because I changed the source code. So maybe you could take in g as a parameter here. And I'm going to implement my gravity simulator. So this is 120,000 generations, 5-second steps, so pretty good simulation. 500 pixel wide canvas, and then 3,000 frequency. So I'm only going to actually draw an image every 3,000 steps. And images have been drawn quickly. And let's see what happens. So if I refresh the GIF, now we'll see some fun behavior where you can see everything starting to get tighter in, although now we actually, and you should run this for more steps so you can see how cool this gets, but we have a slightly stronger force of gravity. So as a result, what happens is things get pulled out and then they get slingshotted around. So the orbits of these things, which started off as circles in our stable circular orbits, When gravity gets increased, we now, especially if you look at Io, it has a more what's called eccentric orbit because it's moving to a more of an oval-shaped ellipse. So a circle is an oval too. It's just one that is perfectly round, but will flatten out. We know that from Kepler's work, we've got elliptical orbits, and so with the force of gravity increased, you would see a tighter pull, and then it would kind of slingshot around Jupiter. So I think this is really neat because you change one line of code, you change just this, and you can see that this whole simulation is only dependent on this one line. That's the mark, not to compliment our own code here, but that's the mark of good code, that you can make one very tiny change and it makes a huge difference. One example of that, just from a completely random off-the-wall analogy here, is something like a great Mario game where the coding is done so well that Mario can jump on a block. I think this was like Mario Galaxy. You could step on a block in the game and it would change the entire level from like a fire level with volcanoes to an ice level, and it changed how you could interact. And there were all these puzzles where you needed to go back and forth between the fire and the ice based off of these simple switches. Imagine how good the code is behind the scenes that allows them to do that, right? And it's because they have very strong code where they worry about, how is it that we can have this so that we can only change, a very small number of lines of code. We don't have to change every single function that we deal with. We just handle this as a parameter, that type of thing. So I think it's cool. The one other thing you really could do and get wacky here is do something like have two galaxies of stars collide. That's going to happen to our own galaxy in a few billion years, I think. We're going to collide with another galaxy, and because the galaxy is sparse, you won't actually see stars collide for the most part, but instead the galaxies will kind of mix and form a single galaxy. If you try to scale up what we just wrote to that example, you're going to start hitting some problems. And the problems, so whereas what we have right now is a very fast gravity simulator, part of why that's the case is that we only have 5 bodies. If you tried to produce tens of thousands of bodies, you'll start hitting a problem. I could leave it as an exercise to you as to why that is, or I will just say now that the reason why that is that when we do call our, I'm in the wrong file, when we call in gravity.go, when we scan through this and we say, where is it that having a lot of bodies is going to create a problem? It's in the update acceleration, because when we update the acceleration of a single body, it's based off of all the other bodies. So to compute the net force acting on a given body, I have to figure out if I have 20,000 objects, I've got to compute the net force that's acting on it according to every other body. So if I have 20,000 bodies, I've got to do this 20,000 times for a single body over 20,000 bodies. So I would wind up with 20,000 squared, okay? So that's going to be a big number. It's going to be a lot of force computations, and I'm going to have to do this for every single update of the universe. The practically minded programmer would then say, why would I do that? Because I already know that the force of gravity is very weak for distant things. We are not feeling the effects of a star that's on the opposite side of the Milky Way galaxy. So if you were going to do something like a galaxy collision, you need some kind of what you might call a heuristic, or a quick and dirty approach that's not going to be exact, but that will allow us to get an approximate simulation, which essentially is what we're already doing. And so I need to only factor things in if they're either supermassive, that'll contribute to the force, or if they're close by each other, right? So if we're looking at stars where they have approximately the same mass, you probably only want to consider the net force, or the force that a star acts on another star due to gravity, if they're nearby. And so if they're very far apart, you don't want to even deal with doing this force computation. There's actually a very clever algorithm called the Barnes-Hut algorithm that manages to organize all of your stars in advance so that you'll know before you do any force computations what are nearby each other in this step, what are very far from each other, and that will organize this in a nice way so we only consider things that are nearby each other when I do my force computation. When I do this ranging over all the bodies, I'm only going to actually factor in a few different stars. So that's really cool. As we learn more about object-oriented programming next time, you could start to head in the direction of being able to implement something like that. For now, that was a lengthy lecture, but always fun to see these gravity simulations, and I'll let you continue to play around with it. Otherwise, thank you so much for joining me. I really appreciate it. And until next time, I'll see you then. Bye, everybody.